around 17 people so far. I think we'll get started. My Nischal.
Hello.
So welcoming everyone to DevDay. So DevDay is a monthly informal event that we do for developers to share experiences, ideas, and opinions with each other. And very recently, we've embraced the virtual style of hosting. So we used to do it at each of our offices. Like DevDay is hosted by Sahaj, and we have offices across Bangalore, Chennai, and Pune. And we used to do it as a monthly informal meeting in the offices on Thursdays most of the time. We're trying to stick to the Thursday ritual, the last Thursday. And yeah, in that series today, we have with us Nischal. And Nischal is the VP of Technology at Omnius. I think he's based out of Berlin. So it must be midday for you, I think. He's here to talk about his personal experience in the last 5 years in the field of data science, which is what today's topic is going to be about, which is taking ML to production. So how I got introduced to Nischal was over a Fifth Elephant panel discussion on problems and challenges faced with taking ML to production. In fact, there is a staggering stat that I came across that 87% of data science projects don't seem to go to production because of the true challenges involved and multiple facets to it. We ourselves at Sahaj have been through some of these, so we're looking forward to learning something more today. And Nischal will be introducing us to something called MLOps, which is like an intersection of data engineering, DevOps, and data science, which will become the norm for engineering teams to follow as we embrace ML models and ML techniques to solve problems. And yeah, that's going to be in store for us today. And a little bit of ground rules. Let's try to stay on mute. And Nischal has said that we can try to work in sections where you can post your Q&A as text on the chat, and we can try to curate it. And during the breaks, we can try to have a more engaging, informal session of more interactions and things like that. So that's about it. Nischal, over to you. Thank you for joining us today.
Hi, everybody. Thank you, Srimati. I'm really happy that you have me here today. And I'm glad it's Dev Day because I am really going to be talking about just engineering experiences, not really anything that's coming from the business side of things or how you have to build your product, and mostly on engineering side of how you can integrate ML and sort of take it into production. I'm going to go ahead and share my screen. Just give me a second. Do you see my screen already? Okay, awesome. Thank you. Okay, I think a lot of you who are working in ML now and are trying to take your systems into production, you come across this normal word that's being thrown around these days called MLOps. And what everybody's trying to do is to sort of bring software engineering principles into machine learning. And of course, it's different because it's not just coded play anymore, right? A little bit about me. So I'm Nischal. I'm a technologist at Omnius, which is a Berlin-based AI company. So I'm the VP of Technology and Data Science there. And you can see me with a snake. I recently had to work on my morbid fear of snakes. So that's my friend's pet snake. It's called Bubbles. It was a very nice experience. So for everyone who has a morbid fear of snakes, at least the small ones don't bite. So I don't know what's going to happen when it grows, but for now it's really fun to play with. Before I get into MLOps, just a little bit of my background. I've been working in data science accidentally for the last 9+ years. So I started off my journey as an algorithms engineer working on building an algorithmic trading platform. I had no idea it was called data science. I was a young engineer who just joined the industry. But I'm very thankful to that experience because it opened up so many different doors. And as most of you can imagine now, everybody's going gaga about AI. And if you're on the internet, I don't think you've read a tweet that doesn't talk about GPT-3 these past few days. Uh, but there's still a very big problem in solving problems that add value to businesses and that add value to products and to take them into production. And at Omnius, we're building a product in the insurance industry where we are helping the insurance companies to automate their claims or claims handling to a certain extent and help them make decisions to resolve claims. And that's our product offering. And of course, the crux of the product is most of the heavy lifting is done by deep learning frameworks and systems that we've put in place. What is MLOps, right? So MLOps is, as Srimati pointed out, it's an intersection of data engineering, machine learning, and DevOps, but not in the traditional sense of how all of these three ecosystems work independently, right? I'm going to be covering each of the topic. I do not have a lot of slides because I want to talk through my experience of what it means to do data engineering, machine learning, and DevOps. And at each of the, after the end of each section, I would like to take questions and try to keep this interactive because um, as one blanket statement, nobody's figured this out in a way that works for everybody. So everybody has their own combination of data engineering, machine learning, and DevOps that works for them, for the product that they're building, for their engineering team, and the skills and the strengths the team has. So I'm not going to be talking about what's the best practices either. So I'm just will talk only about the experience and some of the aspects that you take into consideration when you're doing ML ops, and it starts to vary based on how you want to implement this. So ML ops, as we talked about, is nothing but the science of developing, deploying, and maintaining ML systems in production reliably and efficiently with the capabilities of reproducibility. And some of the verbs and adjectives here is what makes this quite complex and, to be honest, extremely fun because you start seeing how another dimension towards building engineering systems, that is data, changes everything, right? Uh, so we talk a little bit about data engineering first, and data engineering traditionally in the last decade or so, or even 20 in the last 2 decades, you've commonly heard about ETL. So you had a lot of data that was coming in, internet started blowing up in terms of the number of people who started adopting the internet. You saw the emergence of e-commerce systems and everything, and all of the other companies that went on the cloud, and people wanted to know how their systems are functioning. So business intelligence started becoming a very important part. And ETL, which is extraction, transformation, and loading into data warehouses where you build dashboards, um, uh, sort of became the DNA for a lot of companies for quite some time. You saw the emergence of systems like Hadoop and all of the other systems that were built on top of it. But we're going to be slightly talking here a little bit differently about data engineering, where we're talking about data transformations in the context of machine learning, right? So when you're doing machine learning or when you're building machine learning problems, you're trying to fit in very simple terms a mathematical equation to the data that you have at hand. And what kind of mathematical equation you want to fit depends on the problem that you want to solve. And what you do with the data is you do a certain set or certain aspects of transformations on this data to train the model. And training the model is very different from prediction because the kind of data transformations that you would do would probably be batch wise. And depending on the size of data, it could be about how you load the data, how you do memory management, how is it stored on the file system or on a database or a data store, object store, different ways where you would do a series of transformations in steps before the model is actually trained. And this data pipeline is also quite important because it has to be quite robust in handling this data, because you're not going to be training the model once. You will be using the same pipeline to retrain the model with more and more data. And if you're building a product that has machine learning or deep learning as its core, you would ideally be not looking at one model. So you'll be looking at different models, and each of the models pipeline can be different, or data transformation can be different in terms of what this model is supposed to do. When you're looking at this, your data pipelines have to be quite flexible for training, but they also have to be quite robust. And if, in the sense, if it were to crash, and it does a lot of times, you should be aware why it crashed and what you can do in order to avoid such scenarios. So you build a lot of alerting and monitoring in terms of how these data pipelines are built. Now, when you look at prediction, it's a whole different ball game, because in the idea of training the models, you probably have a lot of time to build these models, and you can figure out if something is wrong so that you can fix them. But in terms of serving, the data pipelines are quite different, because you're looking at different volumes of data that are coming in real time or near real time, if that's your use case, or if you're doing a batch-wise transaction here as well, on how to serve the predictions. And during this time, you're still transforming your data, because the data that you're getting in is quite different from what you need to feed into the models. But you have to ensure certain SLAs with regards to the transformation. You need to identify if the data that's coming in is worthy of being transformed, or if it can be predicted based on the models that you have. And we will see a little bit of this later in how do you look at the data that's coming in, and we talk or we touch on the points of data drifts and concept drift. But that's another set of pipeline that you deal with when you're serving models. And if you have N machine learning models, you have N pipelines that are coming in that are predicting, and they also have to scale. So for example, if you're handling 10,000 requests a minute, and that's your SLA, and now your entire system or your consumers expanded or they grew, you have to now scale your predictions, because your predictions are going to take more time if there's more traffic that's coming in, and your data pipelines have to scale accordingly as well. Now, one of the core aspects of data engineering here is that there is all your pipelines, everything that you write is code, and code that we all know can be versioned. But now this code is manipulating data and working with data. So you sort of need to have a handshake between the code and the data that's coming in. So bringing in the concepts of data versioning and data schema versioning is quite important. Now, as data scientists or machine learning engineers or data engineers or anybody who's working in the side of data, you commonly hear this, that the training data that we worked on and the data that we have in prediction, the schema changed. And because of that, all of the requests for the past few days failed. We didn't know why this changed, and we have no idea why the data pipeline broke. So now you need to think about a way to sort of look at versioning this handshake, and it's different based on different mechanisms that you want to implement, so that when the data comes in or sort of the underlying data schema changes, some alerts are already triggered, where you say a data schema has changed in the training, or the data schema has changed when you're getting in prediction through the data pipeline, and this is not what the model knows how to work with. So you tie up a model, the metadata of the model in terms of what schema it's trained on, and the data that it's actually coming in for retraining or prediction, that go hand in hand. And one of the other core aspects of data engineering here that is quite tough to do is data validation itself. So if you're working with a lot of data, and especially unstructured data, it gets harder to do data validation as your data grows, because there is only so much bandwidth that a team has, or the monetary capacity that they have to sort of provide this as ground truthing jobs to somebody to look at the data, to validate them. So there are some interesting ways that you can incorporate in validating the data or ground truthing the data itself. And you need both of them quite done in a flexible manner. And if you want to talk about annotation of data itself for structured, unstructured data. There are some very interesting examples of how you can do this in a very short period of time. There is a product called Prodigy by the creators of, I think, Spacey, who have some very interesting ways to sort of annotate the data. And when you annotate the data, you sort of create metadata for the data that you have. And you need to validate this too, because once your models are trained on this data, they are going to be expecting that when you predict, the data that's going to come in is a sort of this in a similar manner, right? And this entire ecosystem has to be built for a lot of work that you do that go hand in hand with code, data, as well as the schema that's put in place. And if some of you have been following the roots of protocol buffers and Kafka streams and sort of how you implement gRPC, so there's this thing called as IDLs where you sort of define interfaces, and these interfaces are implemented on both the client and server, and they are version 2. So you can manage and maintain versions in different ways for data. And this goes with the data that's sitting on your database as well. It might have gone through an ETL pipeline to be available on a data warehouse, and you would probably take the data from the data warehouse and transform it into a different form before feeding into your machine learning model. So the complexity sort of increases as in when you deal with a variety of data, the size of data, and the problems that you actually want to solve with machine learning. I think I would like to take a pause and try to see if we have any questions regarding data engineering that we would like to discuss about. If we don't have any questions, then I would move on to the next section, which is DevOps. Okay, cool. So we can go ahead. Yeah.
Small thing. There was a request from one of the participants to go a little slower. I think.
Okay. Okay, I'm very sorry. So okay, I'll try to go a little slower. Okay. On the DevOps side of things, DevOps sort of grew again with the whole boom of e-commerce and microservices and sort of having to have systems and services to be running at all times. And with this came a lot of pager duty scenarios, right? So systems would go down at different points in time. They would go down for load. There would be adversarial attacks. There were so many different aspects, but this entire ecosystem started becoming robust over the last decade. You had a lot of tools that came into place. You had the emergence of frameworks such as Mesosphere, Kubernetes, that helped and relieved a lot of stress on DevOps engineers. But with the advancements in machine learning and AI products, DevOps plays another important role because there is no answer to how you can do DevOps depending on the scenarios that you work with, right? So one of the primary aspects of the DevOps in MLOps purview is that you still need monitoring, and monitoring here you're looking at prediction monitoring. So you're looking at how good your predictions are, what is the confidence at which you're predicting in the live systems, what are your SLAs, and how much of network latency is something that you look at through the data pipeline transformations itself. And you need to build monitoring, you need to build dashboards around this, you need to build alerting if something is not okay, so that the data science team or the product team can take a look at. And this feedback is continuous. As and when your product evolves, the monitoring aspect around the data science would evolve as well. The other aspect that is quite hard to do is deployment and rollback strategy for your code and your models. So for example, at time T, you train a model X and you take that into production, right? And at time T plus X or T plus delta, you need to retrain the model. Now you would retrain the model with probably the older data that you have and all of the newer data that you predicted on that you fixed. Now you have a new model, right? You do the validation with the validation data set that you have, and you come up with the idea that this new model is better than the older one, at least in the training ecosystem, right? Now you graduate this model into production. So when you do this in production, you realize that your model is actually not as good as what you'd expected. And you do not want to also send 100% of your traffic into this, into the new model. So now, apart from managing your code and your pipelines and controlling different versions of them, you're also now have to bring in the capability to have control of your models and sort of think about model graduation. And if something is poor and you want to be and you want to roll back, you need to build this mechanism. And building this mechanism with a lot of code and having manual intervention takes you only so far, because you can't really have people monitoring and doing this all the time. So you can build in certain checks and balances based on your monitoring to roll back accordingly, right? Um, then there is this whole issue of infrastructure itself. So we're talking about mostly microservice architecture systems that can scale independently. You have that on the prediction side, but you need that capability even on the training side. If your data size is increasing, you might require GPUs to train your machine learning or your deep learning models on. How do you build this infrastructure? How do you abstract the complexity of the sizing and resizing so that your data science team and data engineers can make use of your infrastructure quite well? So there is no silver bullet here. From our experience at Omnius, we've been adopting Kubernetes for the last 3 years. And to be honest, we're quite happy. So there's always a steep learning curve in understanding Kubernetes, and as in with any other infrastructure management tool. And we've built in a bunch of policies in the way we do training of machine learning and deep learning models itself. So we have the policy of resizing and scaling our training nodes based on the data that that is coming in. So we also have the capability to provide and share GPUs between different clusters of our training instances. And we've done this in a way where our build graduation and our training is sort of independent. So our DevOps layer and the infrastructure tooling that we've built is in a way that the data scientists and engineers can work with it. But the most important aspect here is that you can't really have your DevOps team, your data engineering team, and your data scientists sitting as separate teams. So one of the success factors behind achieving good MLOps is that you need to have cross-functional teams talking together and working on this, because a lot of education has to go in different ways. So data scientists bring in the notion and the idea of how they want to work with their data. What are they expecting as configuration parameters? How this changes and evolves over time. And data engineers are really talking about handling data pipelines and and the entire ingestion part of it and how that needs to scale. DevOps is bringing in the idea of talking about infrastructure sizing, availability, SLAs, monitoring, and alerting. So if they're sitting as different teams, uh, the communication actually becomes a barrier, because they're only learning of each other through issues that are raised, rather than sitting together and working on a solution that works for the team and that they can make that solution available for other teams as well. Um, we had this problem too initially at Omnius. So when we started off, we were quite a small team and our team size grew. And we decided to have two teams. One is the engineering team, which is the data engineering, DevOps, backend, front-end team, and the other was the data science team. Also because we were sort of in a research and development phase, and then we still didn't have a fully built product for the insurance industry. Within 6 months, we started seeing a whole lot of things failing on the MLOps side, because the tasks and the sprints for the data science team and the tasks and the sprints or Kanban for the engineering teams, they had all the tasks, but they never came together, even though we had built graduation sort of a process in place. Stories did not move together. And you started seeing that the data science team did not really understand the approach that was taken by the engineering team. And the engineering team never really understood what the data science team wanted, even though we were a team of 10 people, right? Because people are focused on the tasks that they have at their hand rather than thinking and looking at the bigger picture as a team. So we implemented the concept of squads, tribes, and chapters, where we decided to have cross-functional teams. So it's sort of a new take on matrix organizations, where we had different missions for each of this team on the MLOps side and on the product side itself. So they were building the product and along the side, building a lot of MLOps so that we could scale with our product. And that really helped because for two things. One, people started talking to each other. So the number of issues we saw and sort of integrating the entire MLOps to our product reduced. And two, the knowledge sharing was quite important. Finding somebody or finding engineers who have all the skills, who can do DevOps, who can do data engineering, who can do data science, take that into production and think about the product is actually very unfair to ask of any engineer, because people like what they are doing. So some people are really happy about doing data engineering and DevOps sites. Data scientists are really interested in solving data science related problems and machine learning problems, and it's not in their experience or skill set to know how to do Terraform scripts. They don't know what Ansible is because that's not in their domain. They don't understand, or they've not come across things like Kubernetes. So when we started putting them in these virtual sort of cross-functional teams, they understood why it's important. They understood how the relevance of these systems have to play together, because if they have to take their models into production, they need to know what sort of guidelines that they have to conform to. So my take on a lot of these things is, and I hear when people are building data science teams and sort of product teams, that the data scientists do not want to know about Docker. The data science team, data scientists do not want to work with Git, right? And you have the same sort of learnings you get from data engineers and DevOps engineers. But when you put them in a team together, they start looking at the bigger picture, where tooling just becomes a way to get things done, and the approach and knowledge sharing of why this tooling is required sort of takes the bigger picture. And one of the other aspects of looking at DevOps, data engineering, and machine learning is that you have to really think about this, especially if you're building products, as product as one of the most important things, and all of these different parts are gears that make the product come together. So when you put them into the idea of squads, you also have product owners who are really talking about the entire thing from a product perspective that brings all of these pieces together, right? That's definitely worked for us, and of course, it was not a silver bullet, and there's a lot of management and engineering aspect into getting different things like squads, chapters, and tribes to work. And if you're interested on how to set up teams that way, you can feel free to reach out to me. But you'll see a lot of content that's coming out of the team from Spotify, where this was sort of engineered and exchanged. So there's a lot of content there, and it's very interesting, especially if you're building data science teams that are sort of cross-functional in nature, right? Um, I see that, okay. Um, um, okay, so there are two questions before I move into the machine learning part itself. Deployment tools in ML, you can see certain tools such as DVC and there's ML Flow. What we've done at Omnius and some of the experience that I've had the last 5-6 years is that try avoiding building your own tools, if as long as at least if you don't look at the open source market and something that doesn't already exist there, right? Um, we implemented a lot of things with MLflow, like the data versioning and the modeling in itself and all of the artifacts. For the deployment part of ML itself, we do a sort of model graduation. So we have two different ecosystems that we've implemented. One is a training ecosystem and one is an engine ecosystem. And we've implemented very simple protocols on how we want to move models around and how we can move back. And we have like an artifacts where we store models. MLflow, I think, also supports deployment of models and versioning. You should definitely take a look into that. With regards to the question from Sridhar from about monitoring drift from data schema verification, it's definitely part of drift in itself. The idea of data schema verification is that you can have drift in production or when you're doing prediction of how the data is changed or the schema of the data is changed that's coming in, but you can have the same problem during the training as well. So you can have a problem where if you have, for example, if you take the likes of companies such as Delivery Hero, Uber Eats, DoorDash, and all of these other companies, every microservice, and you have hundreds and thousands of them that are put in place. They manage their own databases as well, and they all have ETL pipelines that bring the data into a data warehouse, right? That data that they have that's sitting with each of the microservice that can change, and the data schema can change entirely there. So you're talking about connecting all the pieces of the puzzle together, where if the data schema changes in your core data creation systems, you have to be made aware of it, because then your ETL pipeline or the pipeline that brings data to your data warehouse changes. And then the data pipeline there would break in terms of the machine learning data pipeline that you've built for transformations. So you have data schema validations that play a big role, not just on the machine learning side of the data coming in, also on the data sync of that is used for machine learning. We will be talking a little bit about data drift as well in the next section, so I can cover a little bit there. Okay, so how do you determine model graduation? Okay, awesome. So I think I will cover that question for sure as part of concept drift and data drift and looking at machine learning models in production. But ideally for model graduation, I can at least answer the first part, is where you have a validation set or a holdout set that you think depicts is a sample set that's never used in training at all, and you try to keep this set consistent. Because what happens over time, especially with machine learning models, is that if you use your if you held your validation data set out of your training set for training of the first machine learning model, and the validation data set changes for your retraining of that model, you're never comparing apples to apples and oranges to oranges here, because your validation data set changed, and you can't really say your new model is better than your old model because your comparison strategy is wrong. And I will cover a little bit about evaluation as part of the machine learning discussion as well. Is you really need to be consistent in terms of how you do model evaluation. And based on that, you can build triggers on how to do model graduation. And the same way in prediction, you can roll back based on similar triggers itself. Okay, so for machine learning here, I'm not going to be differentiating between deep learning, for natural language processing, computer vision, machine learning, anything that you do with machine learning, right? The previous question actually set a very good context here, is your model evaluation. And I've seen a lot of times that this is where things can start to go wrong, because how you partition your data set for training in terms of what's your training data set, what's your validation data set, how this training data set changes over time, how your validation data set changes over time, how are you comparing different types of machine learning model. This is very hard to achieve And it took us a while, even here at Omnius and the previous organizations that I was working with, is it's very hard to understand how your business can change and how your validation data set changes as well, right? So you need to really have a very strong strategy here in terms of how you consistently maintain a good validation data set to evaluate each of your machine learning models. Now, if you're using just one machine learning model, the next point might not make a whole lot of sense. But when you get into this whole field of machine learning models and building products in this space, you end up chaining a set of models. So if you look at using products, e-commerce products, right? If you use Paytm, Flipkart, and all of these e-commerce products, there are different machine learning models at play there. There's a different machine learning model for your search. And if there aren't enough relevant searches that are coming in, you see that people leave the system quite easily, right? So you need to ensure that relevant searches are in place. And of course, there's personalization, which is a completely different aspect. I'm talking about simple search queries. And when you see these search queries, you see the products that are at display. Now, if someone clicks on the product, you see if you want to give a discount, and there's a whole lot of other machine learning that goes into play. You sort of start chaining different machine learning models here. Now, when you do this, the complexity of your problem for evaluation changes because you're not looking at evaluating the machine learning model from one dimension. You're looking at what does it mean for end-to-end evaluation. I'll talk a little bit here about what we do at Omnius because our end-to-end evaluation here is quite complex for us because we are talking about straight through automation rate. So we get a lot of unstructured data in the form of emails, scanned documents, pictures taken from WhatsApp, forms that are filled with people who've written handwritten text, and we deal with different languages as well. So if you just take Europe as a continent, every country here speaks a different language, and they have a different form of layout for the same set of documents. And to deal with this uncertainty is quite hard. Now we have a bunch of different deep learning models that are at play, and what the customer is looking for, the insurance company is looking for in the end is how much of the traffic that's coming in can be automated. Now, when you think about this, every machine learning model is, even though it's being trained on the same training data set, they're looking at different aspects of the trained data set. And in the end, they have to achieve a task. The product has to achieve a task that can be solved using a chain of AI systems. And when we do this, um, we are not looking at evaluating just one machine learning model. We are looking at bringing in concepts such as tolerance band, where we say for a certain tolerance band, this is the throughput of automation that you can achieve. And when you take this tolerance band into consideration, there is also an aspect of error. So when you're building these products, what we commonly don't talk about is AI taking over everything. So we're still talking about human assisted AI here because your predictions can be quite poor. You can be predicting with very high confidence erroneous things. You can be predicting things that you think is based on the training data that you have. You're quite confident that it's the right prediction. So you take a lot of these things into consideration and you sort of build different types of tolerance to evaluate your end-to-end pipeline. And this is a big task because it's not very convenient to do. And based on your end-to-end evaluation, you sort of build triggers into a chain of different models and different versions of models that can come together that you would graduate into your production environment, right? Then you talk about model versioning here. So model versioning is actually that's been spoken about for quite some time. DVC and MLflow do a very good job in helping you do model versioning. So they help you version your model, all of your artifacts. You're looking at things like confusion matrices, and all of the other metrics that you want to use for the machine learning model that you're using, that helps you evaluate each model quite independently, and can also give you the capability to chain different versions of models together quite conveniently. As part of a machine learning team, it's very important that when you start off, of course, a lot of work might be in your IPython notebooks, and there are ways to take your notebooks into production as well. I would not vouch for it, but in case you are a team that does that, good for you. As a data science team, it's important to think about building packages and building SDKs for your own team, so that a whole bunch of you are using similar ways to measure systems. For example, we've built quite a few packages here at Omnius for our entire evaluation strategy, right? So all of our machine learning models, our deep learning models that's working with computer vision, natural language processing, we're working with structured data, semi-structured data, all of them go through the same evaluation package and evaluation methods that the entire data science team is contributing to. And the reason why packages are good is that if all of you are using one code base, so which means that you can identify bugs quite easily, and it's quite fast as when you grow as a team, that you can start reusing them, knowing that a lot of eyes have gone into the evaluation of this code, and it gives you the capability to scale. So really think about building a lot of toolkits and packages and sort of documentation around how to do evaluation for your entire team, and that helps quite a bit as and when you're growing as well. So apart from this, a whole lot of this is being done on the training side. There is a lot of evaluation of metrics that needs to go when your model's live, right? So you're looking at here, if the data that you've received for prediction is very close to or similar to the data that you've used in training. Is the prediction that you're doing right? So which means that if you have huge volumes of data that's coming in, you cannot actually expect to get ground truth for the prediction, right? So nobody's going to validate your prediction. So people, for example, if you're using a search engine and your search engine's poor, people are not going to identify what should have been the relevant search results, right? So they're just going to drop off your system and use another system. So you need to think about metrics as a data science team on what will help you identify if your model and if the data that's being fed into the model is appropriate. And if the more holistically you think about how it sits together for a product, then you have much more power, because product has metrics. Product has metrics in terms of like looking at what's the churn rate, what's the click-through rate, how many people are using the system, what's the volume that's coming in, what are the errors. And if you understand for each of these different metrics and KPIs of the product where your machine learning model is fitting in, you get a better idea of figuring out what's going wrong. And when you work as a team, then you work with the DevOps team and the data engineering team to tell them that these are the metrics that you're looking for as a data science team, and they have to build in alerts and create and help you build dashboards so that you can figure out if you're doing something wrong, and it gives you the capability to improve your models. And all models have to be improved over time, but also gives you the capability to explain when something is going wrong to your customers so that they know how to work with this with the human workforce that they have, right? We will go into the next section where we're going to talk about how we look at models in production itself. I see that there are no questions yet, so I'm going to jump into this section, but a quick time check. Srimati, how much time do I have now? I know we started around 3:10.
So we had scheduled this for a couple of hours, so we do have some time. I think we were shooting something from 1 hour to 1.5 hours.
Okay, cool. Sure. Okay, awesome. Okay, cool. Thank you. Okay, so I think I can answer Sridhar's question here about drift, right? So I think it's expected that the sample data that you trained on does not truly represent the population. So which means the live traffic that's coming into your system is going to definitely be different most of the times than what you've used in training. So now when this happens, your models, of course, if you're lucky, it might predict quite well if it's trained well and it knows how to handle certain diversity in terms of the data that's coming in. But most likely, it might not. So you have to build in mechanisms to understand how your data is different. So you can go from looking at certain concepts such as scale divergence, which you can build to see if your data is different in that you're getting in prediction versus the ones that you have in training. If you're working with unstructured data, you can look at aspects such as vectors itself. So the input vector that went into the prediction of your models can be quite different from the entire vector base that you have for your training data, right? Now these mechanisms and these different plays of looking at how your data is different is going to be quite challenging and different based on the problem that you want to actually solve, right? You have different distributions of data as well. So a lot of statistical inferencing can go in between the data that you have in training versus the data that you have in prediction or you have for production, right? So data drift is going to happen. And you have to build in circuit breakers. You have to build in the capability in your systems to know that the data is quite different from what you used in training. There's a whole lot of literature and tools and things that are implemented to do this. But you have one big problem when your system's live. It's how do you generate ground truth for system that is live, right? How do you know if the value that you're predicting is correct, and how can you get the correct value for the prediction that you've done so that you can do the retraining? That's a very tricky business to get into. So it depends on how you positioned your product. But as one of the aspects as a data science team is that you can't shy away from doing ground truth yourself. So you look at the predictions that's coming in live in your system, and you will try and sit. That's where domain knowledge plays a very important role, because if you try and build machine learning models without understanding the domain, you don't really know what you're looking for. You will rely on just numbers. You'll say, if you're doing classification, say, okay, my F1 score was good in training, so I'm going to expect if the model is predicting with a confidence of greater than 0.7 or 0.8, I will always be right. But that's untrue, because new data, your model is going to be confused. Your model can have overfitted the data. It could be underfitting the data, right? So as a data science team, domain knowledge is quite important because it also helps in identifying features that go into your training and identifying features that you want to use for prediction as well. And you will be able to identify a statistical difference in the distribution of the features itself. For example, if you're dealing with numeric data, right? And you have numeric columns of data that is present, you know that for certain values that come in, simple metrics such as min max, right? So what's the minimum value that you've seen in training? What's the maximum value that you've seen in training? And if the new value that's coming in is different, you know that the prediction can vary. But because there are a bunch of different features, you look at the entire feature vector itself and try to compare if the feature vector that you're getting in prediction is different from what you have that you used for training. So if it's not, you also need to understand what these features were. And you have to look at the data that's coming in, and a whole lot of time will be spent by your data science team in identifying a subset of these predictions and fixing them so that you can use them for retraining, right? Some of the constant things that you can do if people are fixing your errors or mistakes of prediction uh, in your live system is you could do active learning, you could do online learning as well. If you have a lot of data that's coming in, you look at retraining of your entire model with all of the data that's coming in. So you have to build in tools to do the validation. A lot of times you might not even know what the right value has to be. And that's where product, domain knowledge, data science, or basically the entire team have to figure out how to do this. I would again touch on the point of looking at tools from companies such as or products such as Prodigy AI and other companies that are building quite smart annotation tools that people can annotate and fix the errors quite conveniently. So that would be one of the aspects of looking at fixing your predictions and validating if your prediction is right. I hope, Amit, that answers your question as well. Of course, the next aspect is you have SLAs. You have SLAs not just for your product, you have internal SLAs for your model, and you have SLAs for your data. If your data that's coming in for prediction is far from the distribution of the data that you've seen in training, you immediately have alerts for this. And you have SLAs that says the divergence is too much and you have to figure out what's going on. You have the same thing for checking the quality of the model. So there are interesting mechanisms that you can build in where if your data is changed over time and your model is changed, is trained from a previous point in time, you can see how the predictions vary as well. And based on which it gives you alerts to say, okay, this is time you have to start retraining your model, right? So the question always is, when do you have to retrain the model? And you can build in SLAs to check when you want to start the retraining of your model, when you have sizable data that you've predicted on and that you've corrected, or if your model is actually diverging. And on this, I would like to touch the concept of concept drift, where, for example, if you're building a fraud detection system, right, and you've taken your data over the last 5 years, and this data is coming from a point of sale system where people were using their credit cards or debit cards, and you had a point of sale system where they would go into physical shops and they would buy, and people would forge these cards, right? They would forge these chips and they would use these chips in different parts of the world, and your model is trained on the data to figure out what was fraudulent or not fraudulent. Now, let's move in time, and the pandemic situation kicked in. A lot of these systems went online. Now, online behavior of cards are different because the data that you're looking at is not really through tap-in systems, but through credit card number generations and CVVs and expiry dates and all of the different uh, data features of this card that change. So your concept of your business actually changed. So your older model is not capable of predicting if a transaction is fraudulent or not, because the nature of the business entirely changed, right? So that's one of the aspects of knowing how your business is changing so that you can take that into account as a drift in the concept of how you're using the model itself. The other way of looking at concept drift that you would also normally hear if you look at certain talks at various conferences is that e-commerce, for example, if you've trained a model to predict what kind of clothes a user could actually pick up when they do a search, and if you've trained it entirely of looking at data during the summer season, your model will fail miserably when the same user is searching for products during the winter season, right? Because seasonality is a trend that your model might not have picked up on quite easily. So this gives you, so when you're looking at product metrics, you immediately see that you have churn rates, people are dropping off your system. And this gives you a mechanism to say, okay, there's something going wrong with your models. It's quite poor in predicting what the users want. And a lot of these users are dropping off the system. And you understand that seasonality was a very big part that was not taken into consideration. So you might end up having different models for different seasons. So depending on the nature of business that you are in and the problems that you're trying to solve, you have to sort of forward look in what could be potential concept drifts that can happen. And this gives you checks as well in terms of when you can actually retrain a model and how do you enrich your validation data set to take this into account so that you during the training you're quite aware of certain conditions on when the model can function well and when it might perform poorly, right? um, on this, when you have models in production, and I would like to stress on the idea of cross-functional teams, is it's very, very important to know that a lot of these problems cannot be solved by one member or one team that has just certain skill sets of just doing machine learning or just doing data engineering or DevOps. So you need to bring groups of different people together with different skill sets so they can look at how they can build this quite together as a team, and this will evolve too. So there is no silver bullet for this. Your business will change, your people will change, your data will change, your models will perform well for some time, then they will deteriorate. So you have to constantly track this. So this is not something, so data science is like especially models in production is like a relationship that you have with your partners, right? So it has to evolve over time. So there are different things that change, and it's not something where you say, okay, today I built these tools, I built these models, the problem is solved. So if you're taking ML into production, it's going to be a long journey, and it's going to be a journey where things will change. Your models will sometimes completely break, and you might actually be using a wrong approach because you made an assumption based on the training data set that you had that these were the models that you wanted to use for solving the problem. And if you're working in data sensitive space, which I think is going to get more and more relevant because you will not have access to data sets. So you do have models that you can train against public data sets, right? And you say, okay, your model is quite good because against this public data set, you have metrics, which is quite consistent with the state of the art models that are there, and you know what you can expect. But the problem with public data sets and your actual model in production when you're working in sensitive environments is that your sample set does not even remotely qualify to the population. So you have to uh, expect that your data that's coming in for prediction is going to be completely different from the data that you've seen in training. So how do you handle that kind of environment? So building in human in the loop sort of systems, especially when working with sensitive data, is quite important, because if you look at new data that's coming in and you know that there's a data drift between what you have used in training, so what you see in production, you can immediately route that to a human who works on this data and builds uh, the ground truth for you so that you can use it for retraining. Um, and you will have anonymized data that's coming in because you will have to predict on anonymized data, and that is going to be a lot of that's going to be hard as well. And if you have systems that are open to the internet, you're looking at adversarial attacks that are coming in on your model, and you have to figure out how to work with adversarial attacks that are coming in. So uh, machine learning model building machine learning model products or products that use machine learning models is uh, is going to evolve, and MLOps is a field that we will see that will grow leaps and bounds in the next years, because the amount of power we are going to give these models, or the amount of decisions that these models have to take and make, are going to enhance across all industries as well. So it is going to be an interesting journey to see. We've implemented a few things in understanding concept drifts at Omnius. So what we've tried is that we have thresholds or tolerances as configuration parameters. So the moment we see new data that's coming in, you can expect your models to have very poor confidences in terms of its prediction. So that's already telling us that this traffic needs to go into a human, so or humans have to verify. The cool part with building a system this way is that you might not be wrong about all the predictions that you do. So this makes the entire annotation process or the quality check process for the predictions that you do quite convenient, because if you have, let's say, for example, you're predicting 100 different fields, right? And you're okay with 70 fields, then the corrections are on just 30 fields rather than all the 100 that needs to go in. So you will end up predicting on this data, but you will send it to a different route so that humans take a look at it. And if they say these things are okay, 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 and these things are not, and they correct, that sort of becomes a training loop. So you have to take that into account. How do you do training and retraining, and when you can actually uh, prompt your product teams or your customers to do the retraining. And it's actually quite complex and fun to do. So you see that all your assumptions start to fail every 3 months. So you have to come up with new hypotheses, new assumptions, and build more circuit breakers into your product. And that sort of evolves over time. I see a few questions. So from Rohit, it says, for a product company, data is reasonable or strained on its complete. Yeah, so Rohit, I think I sort of touched on this ideas. Uh, it's quite hard. So if your data is strained uh, due to data availability reason, which is something that we face on a day-to-day basis because we're working in the insurance industry, and all of the data is confidential, one. And two, um, they're not going to push the data to the cloud either. Three, they're not going to work with a company that they don't have contracts in place or NDAs in place. And four, even if all of this is in place, they do not have access to all of their data either. So the data is distributed in various systems. So they're always going to give you a fraction, and I say a fraction, really a minuscule amount of data that you can train on. But the only thing that you can do is that you educate your customers with this. So when you're shipping your product and when you're selling your product to the customer, education on all sides have to be important. So you have to internally educate your own stakeholders. You have to educate, as a data science team, you have to educate your product on the pitfalls of looking at this data, on pitfalls of this model. You have to educate your leadership team and your sales team on how and what they can sell this product to the customers. Once you've sold the product, you have to educate the product in terms of educate the customers in terms of what they can expect with this AI service and where do you draw the line. And you have to tell them that the model is going to get better, the model is going to evolve, but because of the training data that it's seen, the predictions are going to be scattered. Some are going to be good, some are going to be bad, but over time this will evolve. But we give you the capability of knowing that this data is different from training. We give you dashboards to understand where this is failing. We will translate all of that data science knowledge into Excel sheets, into graphs, into Tableau dashboards, into different kinds of dashboards that your business teams can work and operate with, so that you know how to work with these systems, and you know there are triggers that are telling you that you need to retrain on. And don't think of AI systems as a way to sort of fire your highly qualified manual workforce, because you can use your highly qualified manual workforce to do more complex tasks, and you can use them and help them. Use is an unfortunate bad word, but you can actually work with them to sort of enrich the predictions that are coming in. So these models can do all of the mundane heavy lifting tasks, and your product can evolve over time. I hope that answers your question, and if it isn't answering your question entirely, you can please feel free to reach out to me, and I can go through some instances that we've done here. But I don't really have a concrete answer that says this is exactly what you can do and avoid the situation entirely, right?
In these data unavailability cases that you mentioned, Nischal, with some of your customers, the
Yeah.
human in the loop solutions are baked into the platform. Is it how to recover from a wrong prediction and retraining? And
Yeah, so everything is built into the platform. So that's where, so for us, MLOps is not something that we use internally. So MLOps is built into our product itself. So when our product goes into our customer, especially because we are in a B2B environment, um, you have to give the capability for your customers to use a complex product or a product that's using AI in a way they would use any normal product. So we've sort of, even though our product does more things than just the ML part of it, we've built in the MLOps capability there. So they can look at evaluation in the training ecosystem. They can look at doing end-to-end evaluation across validation data sets. They can create different types of holdout data sets. They can look at when the system's failing in production. They can see the distribution of the predictions and the quality that they have. It builds, and you can give them triggers to retrain, but you have to constantly build education around this. You have to sort of maybe build videos, build documentation, sort of go there and do workshops. And this is something that is challenging, and it's also quite expensive, but you realize you have to do this, especially when you have scarcity of data that's coming in that you're working with. We have a question from Sridhar, where you have thresholds for every incoming feature. Sridhar, it depends really on what you're trying to do. For example, for us, because we deal with only unstructured data, we are mostly looking at vectors that are coming in rather than every aspect of the data, because we don't really know if all the information that we want to identify and work with and come to a decision is actually present in the data that's coming in or the incoming. Uh, we don't know if all the features are present. So we try and do vector to vector comparisons to understand if the text that we're dealing with, if the entire word vectors or basically document or page vectors are very similar to the distribution of the vectors that we've seen during training. So if we're dealing with computer vision images where we take the vector of the images itself, you can look at contrast, you can look at saturations, you can look at shadows. There are different kinds of transformations that you can do to identify what features are important. But what I would like to touch here is that understanding and knowing your domain is very important, because when you're building features, even though you're using deep learning or machine learning models, you know what features are the ones that are important, and uh, you build in model inferencing too. So for example, if you're using machine learning models, uh, systems or tooling such as Lime, and you look at activation functions, and you look at activation maps, heat maps on your images. So you know what are the features that are important for you to solve this problem, and you sort of build thresholds accordingly. So you might not worry about every single feature, but you will definitely have to build in certain form of thresholds for a group of features or vectors, and you can also build in mechanisms such as scale divergence to figure out how different your incoming data is to what you've used in training. And it really depends on what type of data you're working with as well. So if you're dealing with structured data, unstructured data, you're dealing with logs, you're dealing with click-through rates that are coming in. So it's quite different based on the problem that you so want to solve for every machine learning model. Um, so this is what your potential MLOps system might look like. I got this off a presentation from one of the cool talks that I saw in 2019 from the data scientist or product owner at Dika. I have the links to the talk as part of the next slide, and I will also share the slide. So all the credit to this image goes to the person who created from that organization. But potentially, this is what your system, if you're building MLOps, could look like. So you have a data store, and then you have feature engineering that you do as part of your training ecosystem, and then you do the training. So you do batch one-off online training, and then you store the trained model in your model servers, and you use from these model servers, you publish them into your deployment cluster where you're doing the predictions, and your feature inputs are coming in that's real time through the data extraction framework. And you sort of have cron-based systems or scheduled systems that you can take a look at, that's identifying the drift between the data, identifying concept drifts. So one of the other core aspects of building MLOps is that it cannot come in the way of your normal business. So your products cannot break down because your features are different, because your concepts are different. So you have to take the strategy of a sidecar approach. Yeah.
Could you zoom in a bit?
I'm gonna try. I'm gonna try and share the slides later, but let's see if I can zoom in. Unfortunately, with the slide thing, I don't think I can. I'm sorry, Amit. I don't think I can, as part of the slide presentation, to zoom in. But I'm going to share this. Actually, you also have a link to, as part of the slides, for a high resolution presentation that has this. But I think the approach here is on what I was talking about as a sidecar approach is you need to build all of your tools that are not invasive in the functionality of your product. So all of your scheduled jobs, your dashboards, your notifications, your alerts, everything has to come in that doesn't affect your product, but that builds in triggers and mechanisms that gives you enough information to know when to retrain, when to your predictions are failing. Um, and you will hear more and more about sidecar approach, especially if you're in the Kubernetes environment and if you're building service meshes as well. Istio is an implementation of sidecar too. So on the infrastructure side of things, how you work with the entire implementation. But that's quite important to know and build as well as part of the team. Um, One of the things that I would like to mention is you don't necessarily have to build all of this by yourself. So, for example, for your data pipelines, you could end up using systems that are there, such as Airflow. So there are better systems that from an organization called as Prefect HQ, which is also quite good in terms of how you build data pipelines. So you don't necessarily have to figure out how to build data pipelines, how to build user interfaces on top of it, because that's taken care of. How to version the models can come from your systems such as DVC or MLflow, or from Databricks or other open source systems that are there. How do you manage your entire infrastructure and scale? So you have frameworks such as Kubernetes that you can use in terms of managing your training ecosystem, basically your production ecosystem. For alerts and for logs and dashboarding, you can have simple alerts and logs that you can push as JSON files into your ELK, build your Kibana dashboards and use them as alerts that can talk to your pager duty services such as Slack, Teams, SMS if you're dealing with it, and if you're from the 1900s, so emails or whatever you want to do with, you can build triggers there. So look and work in the open source ecosystems, use the technologies that are there. I think the power comes in how do you sort of build communication between these systems quite conveniently. You also have, for example, if you're dealing with a lot of data that's coming in and you want to do event-driven sort of systems, you can use Kafka streams. You can handle Lambda architectures with systems such as Spark. And if you're dealing with deep learning systems, you can off the bat use fast.ai, and you can build and and you can even serve your models from there. So don't try to reinvent the wheel until and unless you MLOps is your product and that is what you're building and you want to build everything together. You can still use a bunch of open source frameworks and build your product on top of it. There are a whole lot of products there, and MLOps um, uh, as a topic is gaining more and more clarity. You have the likes of Amazon and Microsoft and Google who are also talking and building products in this space. For example, you could build your entire machine learning pipeline with Kubeflow if you're on the cloud, right? So especially with Google Cloud, and you can run Kubeflow as well if you're on the cloud as an open source project too, without being attached to any of the core cloud providers. So I, by design, I did not want to put a slide of all the technologies that I'm aware of that you can do different things. Um, you just Google for MLOps thing, you will get a whole lot of things that you want to do. And in case you want some certain recommendations, you can always tweet to me, or if you are using LinkedIn, you can find me with Nischal, Harohalli, Padmanabha, or you can find my profile and you can reach out to me or drop me a note. I would be more than happy to discuss a few frameworks that we've used and how you can work with as well. The question is, for evaluation. So Dika actually talks about this product called Orbit, I think, which is for building and working with monitoring. They have a product for data drift and concept drifts, and they help you build min, max, and everything into your product. So there are new products and open source contributions that are coming in uh, for looking at data drift and metrics and models. You could actually quite conveniently build them with logs. So you can log everything through simple logs, your application logs that are coming in, and you can have dashboards to look at them through Kibana, or you can source them through your to your IPython notebooks as well. And you could use matplotlib, scikit-learn, different types of plotting mechanisms that you have. I think it's called as Orbit. I have the link to the presentation and the talk as part of the credit slide, so you can definitely look at it. And maybe I have the name wrong, but as far as I remember, if my memory serves me right, it's called as Orbit. With this, I'm at the end of my presentation. It definitely took more time than I had anticipated for. Um, this is something that you can do. So you can sort of build and do social experiments with your product that can help you generate more ground truth data. And for example, if you looked at the recent captcha images, so people ask you to spot everything that has a signal, things that have cars, things that have roads. It feeds into actually machine learning models because you're generating invaluable ground truth data. So they already have predictions, and they're going to compare if their predictions are right. So as product teams, as engineering teams, you have to be smart in the way to capture more ground truth data, especially on your predictions. And you can build a whole lot of different things as signals and nudges for your users, small things here and there that can help you generate a lot of data. This obviously came from XKCD. So it's a fun way of looking at how you look at annotations as well. I have a few links. I'm starting to create a post maybe on GitHub or on my website for all the MLOps links that I think are convenient. So you can stay tuned. So you will see more and more links and talks that are coming from the industry that I will start tracking. The data council.ai task. So this is the one that was a talk that I was referring to with the image that I had used in the slide. So please check out if you're interested. There are cool slide posts from Google and towards data science about some of the topics that we touched on today. And for the slides design, one of my friends is starting out building a sort of an exploratory company on helping people build slides. You can check him out on Tygo Studios. So he helped me out design these slides. So yeah, that's more or less on what I had around MLOps. And if there are any more questions, I would be more than happy to take them. Thank you.
Thanks, Nischal. Anybody can speak up. You can unmute and share your questions and comments.
Do we gonna have the recording available? Like I joined a little bit late, so I like.
Yes, Ravi. We will be uploading it to the meetup page itself as well.
Thanks.
Nischal, this is Sridhar. I have one question.
Sure, go ahead, Sridhar. Yeah, you're audible. Yeah.
When it comes to reverting back to a older version of the model, how easy is it to revert back in your experience? Because nowadays people talk of one-click deployment. So is it just that simple? If a click to revert back, or you go through a set of processes to get that deployed.
Correct. So I think that's what MLOps is all about. You can achieve one-click way to go back and roll back your models. That's definitely possible. If you okay, so I'm gonna probably name drop a few technologies that we're using and how it's made it feasible for us. We've come to a point where we've been able to go back with one click, and we have different ways to do this. So we use Kubernetes. So basically what Kubernetes does is you have the concept of pods. So you can think about them as microservices, and we load the models in when the microservices start. So when you load the models, we basically not, we just give a mount path or a volume path to these services from where they can read the model, which goes in as a configuration environment variable that you can change in real time. So what we end up doing is that when you change and roll back a model, we spin up a new pod in real time with the environment variable that's changed of the previous model version name. And you have to figure out how you want to route the traffic, because one of the things that we do, we are looking into that can help us route the traffic and sort of ease all the traffic once this pod comes alive is through something called as Istio, which is a service mesh. So you would do the same thing if you were working with building your own load balancer, is you would still be pushing all the traffic to your old service. And when your new service is up and alive with a liveness and a readiness probe, you start directing all the traffic to the new service. And if the new service is stable with the older version of the model, basically you bring that down. But you need to build in a lot of checks and balances here. So for example, if your old model is trained on a previous data schema or a different data pipeline, the rollback is not just for an old model. If you have a chain of models together, it's not rolling back one model, but a chain of models that you want to roll back, because the performance of the system is based on all of these models interacting with each other. But you can achieve one-click rollback if you're versioning your model right, if you're versioning your pipelines right, if everything is basically, I would even go to say containers. So if you have containers version, so your code has a tag, right? And your Docker containers have the same tag, and you have a data schema that's in place where your release of the product is supported with backward compatibility accordingly. So you have semantic versioning, not just for your product. You have semantic versioning for your microservices, for your data, your code base, your data pipelines, and your models. You can revert back quite conveniently. So I didn't touch on release engineering here for MLOps because that is a topic that can go on for hours. So if you want to achieve one-click rollback, your release engineering of your MLOps has to really be strong, like really strong. And once you have that, you can do this quite conveniently.
Thank you.
No problem.
I often feel this one-click rollback is an engineering problem, certainly. But knowing when to roll back, when is that right time, that is the bigger challenge, right? When is your model working for you or when is it not? That human assistance is one side, but then...
Yeah, so I think that's exactly why you build things like PagerDuties, where you're constantly tracking the performance of your model. You're constantly tracking input vectors that are coming in. You're looking at your predictions and the distribution of the confidences of your prediction as well. And these triggers are very important, where the triggers are sort of broadcasted and someone's able to take this call. So normally for rollbacks of models, until unless you're 100% sure, you'd never have this automated. So usually the rollback of the models are done by humans. And if you don't have the capabilities of routing traffic and managing controls, you actually issue a downtime. So environments that are working in a way where you've not built this capability, which is actually, I would suggest is the right way, because is there really a necessity for doing a rollback with one click and in real time, right? So you don't want, so when you bring in a concept as such as that, there is complexity in your infrastructure, there's complexity in your DevOps, there's complexity in your engineering. The question you have to ask is, what is it that you want to solve, right? So if you have these triggers coming in and you have a contract with your customer that you can achieve a downtime, and if you're not an online system that's like an e-commerce system that where you can't really lose traffic, then your customers are okay. But if your SLA is that you have 99% uptime and your SLA is that if models are performing poor, you have automated rollbacks to the previous models, then you have to spend your time on engineering. That's where MLOps plays a role, because MLOps as a topic is quite broad. And depending on what you want to achieve, you can position your MLOps system or platform or design in a particular way.
Yeah.
Okay. Any other questions? I would be more than happy to answer if there are any.
Okay, I guess that's about it. Thanks, Nischal,
Cool.
again for sharing your experiences as well as lessons.
Thanks, Nischal. It was very helpful. Yeah.
Thank you, everybody. Thank you for having me, and please feel free to reach out, Twitter, LinkedIn, email, anywhere. I will be sharing the slides. Srimati, should I be sending the link to the slides to you, or you
Sure,
would be
you can
sharing
send
it
it to
with the
me and
community?
we'll circulate it within ourselves and put it up the meetup page.
Okay, perfect, sure. Thank you very much. I hope all of you are safe. Take care of yourselves and your family, and have a good day.
Yeah, likewise. And if you have any feedback for us, guys, everybody, including Nischal, do drop us a note to make this better, the virtual thing. We're trying to make it better for people to have, a better way to collaborate in these tough times.
Yeah. And if you have any of the topic that interests you and that you want us to cover, you can just drop a note on Meetup link, and we'll try our best to cover that.
Thank you.
Thank you, everybody. Have a good one. Thank you.
Okay, thanks, Nischal. Bye-bye.
Thank you. Bye-bye.